Hey Algebra Bros, in this video I'm going to show you how to derive the library function, the absolute value function. The reason why it's called the absolute value function is probably quite clear. You can see that how we operate on the inputs is as follows. Pick any value of x, and when you plug it into the function, you're going to have to take the absolute value of it. So let's go ahead and start there. Let's go ahead and fill out this table of values. We'll start with x equals -2. You plug that into the function f of x, you're required to do the absolute value of -2, which is +2. And that gives us our first point, -2, +2. Plugging -1 in, we'd have to take the absolute value of -1, which is +1. So our next point on this graph is -1, +1. Plugging 0 in, you're required to take the absolute value of 0, which is 0. So this graph does have a point at the origin. The absolute value of 1 is 1, the absolute value of 2 is 2. So our last 2 points are at 1, 1, and then 2, 2. Of course, you could use more and more x values to get more and more points on this graph, thereby making your sketch a little more accurate, but this is probably enough to infer how this graph is going to go. Let's go ahead and start connecting all these points. We'll start with -2, 2, go to the origin, and then from the origin we'll go ahead and sketch the rest of the graph here. The origin is going to go through, or we'll draw a segment going from the origin through these 2 points as well. And if you were to use more positive x values, you'd see this part of the graph just continuing in that way indefinitely. If you were to use more negative x values, you'd see this end of the graph going up and towards the left indefinitely. And this is what I sometimes describe as a V-shaped curve. The absolute value gives us a V-shaped curve. And it kind of relates to the square function in the sense that the square function is a U-shaped curve. Okay, so that's kind of like the major distinguishing factor of the square function and the absolute value function. The absolute value function is a V-shaped curve, whereas the square function is a U-shaped curve. Okay, so with this graph in mind, let's go ahead and figure out some of the details here. The domain, if you look at the rule of the function, you can plug anything you want into the absolute value function. There's no opportunity to divide by 0, and there are no square roots, fourth roots, sixth roots, any of those types of radicals present here. So for that reason, the domain would be all real numbers. Looking at the graph is fully connected, and it extends outward horizontally indefinitely. In other words, we got one part of the graph going from 0, 0, extending all the way out to positive infinity. Okay, the only way that would happen is if you're using the positive x values, of course using 0 as well. And the only way for this part of the graph to be going up to positive infinity in this way is if you're using all the negative x values from the x-axis. So that's another way of reasoning out the domain. Now as for the range, there is a smallest y value on this graph, and it's at 0, 0. In other words, smallest y value for the range is 0, which we can include. And because both ends of the graph shoot up to positive infinity, we'd be using not only 0 as a y value on the graph, but also any other y value that is greater than 0. All right, so in other words, 0 all the way up to positive infinity on the y-axis, those values are being used as part of the range. As for whether or not it's even or odd, you'll notice that this graph has y-axis symmetry. And we know that any function whose graph has y-axis symmetry is an example of an even function. So this function is even. An analytic approach would require us to compare 3 expressions, one being f of x, the other being f of -x, and the last being negative f of x. Now f of x is just the original expression, the absolute value of x. F of -x requires us to plug -x inside the absolute value. Now this is going to simplify as just regular absolute value of x because it doesn't really matter what we get from having the negative in front of our input. All it's really going to do is just kind of change the sign of the number that's inside the absolute value expressions, and no matter what, when we eventually take the absolute value of it, we're always going to have the positive version of that number. So for example, if x was 5 and we plugged it into f of -x, we'd have absolute value of -5, which comes out to positive 5, which is the same darn number you'd get if you were just to plug 5 into the absolute value of x. And you'll notice right off the bat that f of x's expression is equal to f of -x's expression. And so just from that, we could also determine that this function is even. Negative f of x would require that we multiply -1 to the original function expression, which is absolute value of x. Which what that does is it places the -1 in front of the absolute value expression. And here we can't really get rid of the negative sign because it's not inside the absolute value. This would have to trickle through any of your simplification should you choose an input value of x. So for instance, if we were to plug 5 into negative f of x, we'd plug 5 into here, and the absolute value of 5 is 5, but because of the negative being out in front, we then have to take the opposite of 5, which is -5. So in this case, the negative position does matter. All right. As for increasing or decreasing, the function has both, actually. There are two parts, and one part is decreasing, the other part is increasing. If you trace this graph from left to right, starting with the left end of it, you'd see that your finger goes down on the paper, which means that the first half of the graph is part of the graph that is decreasing. And the x values that correspond to that piece of the graph are from -infinity all the way up to 0. Whereas the second half of the graph, or the rest of the graph, would be an example of a graph that's increasing. Okay, if you were to trace this part of the graph from left to right with your finger would now go up on the piece of paper. And so the x values that correspond to that part of the graph that's increasing are from 0 to +infinity. So this graph does have both types of behaviors. All right, and those are all the details of the absolute value function. Thanks for watching, and feel free to let me know if you have any questions.